Okay, now let's start with the revision for J2 topics today. Now, just a quick introduction. My name is Pamela and I'm Overmarks H2 Physics tutor. So I'll be tutoring for 11 years inclusive of group tuitions and crash courses. So I have weekly group tuitions which I'll put a detail on later, as well as the details for the June holidays crash course, which is actually one of the more important details. Hopefully you guys can take note of it, so later you can sign up on the website as well. Okay, now for today, what we'll be going through for J2s, right? We'll be going through with you guys the content here, temperature and ideal gases, mainly the first ideal gas law as well as the first law of thermodynamics and some of the special processes. Then we'll look at oscillations, mainly your simple harmonic motions, your damped and forced oscillations, as well as resonance. And then we'll look at waves, whereby we'll look at superpositions and stationary waves. And then lastly, we'll revise current of electricity as well as DC circuits. Okay, mainly the potential divider, potentiometers questions, and balance circuit questions. Okay. So how do we actually just some tips on how you guys can actually revise for physics. Just remember, whenever you practice for physics, it's like practicing for math. Practice makes perfect. So before you start doing tutorial questions or your TYS or any types of questions, it is good to actually do a one-page summary for each chapter, whereby you list down all your key concepts, all your key components and formulas that you need to know without referring to your notes. And then after that, you check back again with your notes to see what you are missing out and what are the things that you need to strengthen on. Then of course, do more and more practices, because practice makes perfect. And I know it's a very cliche term, but the more practice you do, the more types of question you're exposed to. So when you face with a question during an exam, right, you won't get like a shock, like, oh, I've never seen this before. This is something new to me. So the more question you do, you're actually lowering the occurrence of meeting new questions. Okay. Then obviously also have your answering techniques, in a sense that always have a very broad game plan of what you want to, how you're going to answer the question. What is this question asking about? What topic am I actually being tested on? Once you have all these little things in your head, right, it narrows down your the things that you actually need to pick up from your database form, and it's not so confusing for you. Okay. Okay, so let's get started first on the first topic. Now, the tips that we're going to go through for temperature and ideal gas, mainly a full revision of this topic here first, is that in ideal gas law or in ideal gas, you need to actually know the ideal gas law equation, which means that any gases that behaves like an ideal gas, right, will follow this main equation here, PV equals to nRT. But in any case, if the question given to you was actually not in terms of number of moles, but instead in terms of the number of molecules, then that's when you use PV equals to nRT. Okay. Next, the kinetic energy of a molecule, you also need to know the kinetic energy of the molecule is derived to be 3/2 kT. But take note, this is for a molecule. Why is this important? Because when we talk about inside a gas wise, there is more than one molecule. And let's say if there is n number of molecule, capital N, okay, then my kinetic energy of my gas is therefore equals to 3/2 capital N kT, right? Now, why is this important? Because you have learned before in thermodynamics that when I talk about an ideal gas, okay, because for ideal gases wise, there is no potential energy, there is only kinetic energy. Therefore, the kinetic energy of an ideal gas is actually equivalent to the internal energy of the ideal gas. And therefore, the internal energy of the ideal gas is therefore the same formula as the kinetic energy, 3/2 nKT. Okay, so this is important. So then the next thing, what determines the ideal gas? In this case here would be your empirical gas law, which is your Boyle's law, your Charles law, as well as the pressure law. So the Boyle's law states that your pressure is inversely proportional to your volume. The Charles law states that your volume is directly proportional to your temperature, and the pressure law states that pressure is directly proportional to temperature. Okay? So that is for temperature and ideal gas law, just a quick revision. Then for the first law of thermodynamics, there are a few things that I need you guys to take note of. In first law of thermodynamics, they split it into two portions. The first part is the calculative part, whereby they need you to understand that when a substance gains or loses heat, whether is it gaining heat or losing heat, it will experience two types of changes. The change will not happen simultaneously. Take note. This one will not occur simultaneously, meaning to say that if there is a change in temperature, my substance will not be experiencing a change in state. If there is a change in state, my substance will not experience a change in temperature. So if let's say your substance is experiencing a change in temperature, then the formula that you're going to use to calculate would be Q equals to C delta T, where C here is actually your heat capacity, okay, and the change in temperature, or MC delta T, where the small c here is a specific heat capacity, where you need to actually multiply it with your mass, okay? And sometimes if the question actually gives the power of something, let's say they give you a heater, then you know heater runs by electricity as well, so there is actually voltage and current involved. So then my heater, the heat that is given by the heater can then be equals to IVT, and that will be equals to MC delta T. Okay? Okay, so then the next thing, if it experiences a change in state, then what would my heat be related to? My heat gain or heat loss be equals to? I can calculate it by equivalating it with MLF. If let's say my substance is changing from solid to liquid or liquid to solid, okay? Then if my substance is changing from liquid to gaseous or gaseous to liquid, then this would be Q equals to MLV, whereby my LV is my latent heat of vaporization. Okay, so that is basically for change in state. Now next, in first law of thermodynamics, you learn that it states that the increase in the internal energy of a system, which is your U, is actually equals to the sum of the heat supplied to the system and the work done on the system. So which means to say that U, delta U is equals to Q that is supplied into the system, okay, or to the system, plus work done on the system. This is very important for you to know, because if let's say I have Q supplied out of the system, then it will be negative Q into the system, okay? And if it's work done by the system, is what you have, then it will be negative work done on the system. So you need to put your negative sign accordingly, okay? Okay, so here are the sign conventions. If my delta U is positive, this means that there is increase in internal energy, okay? But if it's negative, there is a decrease in my internal energy. If Q is positive, heat is absorbed by the system. If it's negative, heat is lost by the system. And if there's work done, the work done is positive, means work done on the system, which means that your system is compressing. It's getting smaller and smaller. And if it's work done negative, that means it's work done by the system is expanding. Okay, so that's the second tip that I have for first law of thermodynamics. Now the third tip, special processes. So in every thermodynamic question, there will always be a PV diagram, okay, that relates your pressure together with your volume to allow you to calculate your Q as well as your W. Okay, why? Because if you guys remember, first law of thermodynamics states that the change in internal energy is equals to Q plus W. And then we have already seen earlier on that Q can be calculated by using Q equals to MC delta theta, Q equals to MLF, or Q equals to MLV. Okay, then work done on the system is calculated by pressure times the change in volume. Okay, or it could be area under the PV graph. Okay, so that's why in thermodynamic questions, sometimes they tend to give you a PV diagram whereby they want you to calculate the work done. then it's up to you to determine whether it is an compressive system or an expansive system. That means work done on the system or work done by the system. But there will be some cases whereby they give you certain processes that are slightly special. For example, the first one is they say iso. Now, the term here iso means equal. So just remember, iso means equal or same. So when I say isothermal process, this means that the temperature is constant, thermal temperature. And if temperature is constant, remember the internal energy of an ideal gas is actually calculated as the kinetic energy. So therefore, this would be 3/2 nKT. So once you understand these three parts, you can then say that if it's isothermal system, then your delta U will be equals to 0. Can you say that? And therefore, your Q would just be equals to negative W. That means your heat supplied to the system is negative work done on the system. Okay? Now, if it's isobaric, iso means same. Baric sounds like a barometer, which is the instrument to measure pressure. So that means pressure is constant. Pressure is constant. What does this affect? Your work done on the system. So as such, your work done on the system will just be a fixed pressure. Okay? Negative P times delta V. And work done will be a rectangular. Now, what happens if they say isovolumetric or isochoric? Now, this is slightly complicated because choric, it's hard to remember. You can remember as isovolumetric, then this means volume is constant. So if volume is constant, there is no change in volume. Understand? Meaning to say, my delta V equals to 0. And if delta V equals to 0, that means W would be equals to 0. Then your internal energy is just equals to your Q, heat supplied to the system. Okay, the next special process is adiabatic. Adiabatic means there is no heat transfer in and out. Means to the system, out of the system equals to 0. So therefore, your internal energy of the system will be equals to the work done by the system. In order to achieve an adiabatic process, you need to make sure that the system is not only insulated, that means it's covered with a protective surface or a boundary that makes it to be insulated, but the change in pressure and volume occurs faster than the heat exchange. Then that's why your work done will be very significant. Understand? Okay. And the last special process, cyclic process. Now in cyclic process, this is important. It is a process whereby in my diagram wise, it will happen as a full loop. So what happens is that you will have an enclosed loop that signify the start and the end to be the same. So for this, there is constant internal energy initially and finally, which means to say that at the end of the day, your delta U is equals to 0. Okay? Because it starts and returns to the same position, so there is no change in internal energy. And as such, we want to see whether is it work done by the system or on the system, we look at the loop. If you realize I change in volume from A to B, which is expanding, can you see that I'm getting bigger? And the area under the graph is bigger than when I compress back from C to D, which is this part here. Then this means that this is work done, positive work done by the gas. Understand? Because it's expanding. However, if let's say my volume is decreasing from B to A, can you see that? And the area under the graph is this big. Then the expansion from D to C, the area under the graph is only this big. Then this is negative work done, which means that there is work done on the system. Your thing is actually being compressed. Understand? Okay. So this is where your thing is being expanded. And that's the other one is where the thing is being, your gas is being compressed. Clear? Okay. Okay, so let's take a look at the first question. Now, it says here, state two basic assumptions about the kinetic theories of gases. This is mainly just to determine, asking you to lead you to the ideal gas law. So, what are two basic assumptions of kinetic theory? Usually, the more popular one that we like to mention, right? The first one being, the gas have no intermolecular forces of attraction. No intermolecular forces of attraction except during collisions between the molecules. Okay, so this is one of the more important assumptions of your kinetic theory because it actually assumes that there is no potential energy for an ideal gas. Okay. Okay, then the second assumption in this case here, we want to actually say that the volume of the gas molecule, this is another key assumption in kinetic theory of gases to assume that a gas is going to be an ideal gas, is that the volume of the gas molecule is negligible compared to the volume of the container. Okay. Now, obviously, there are actually more than two. You can also say that the gases are always in constant random motion. That's one. Number two, you can also say that when collision happens between the gas molecule, it is always elastic collisions with the wall of the containers. Okay, so that's another two other assumptions that we have. Okay. Now, I will upload the completed annotated paper here later up onto the Telegram so you all can download. So if you can't copy in time, it's no worry. Just go through with me. Okay. Next question. By considering the random motion of the gas molecule in a cubic container of length L, so random motion of gas molecule, cubic container length L means length times length times length, show that the pressure exerted by an ideal gas is given by this equation. Pressure of the gas is equals to 1/3 the density of the ideal gas times the root mean square speed, the square speed of the gas atoms of the molecule. So this is actually a derivative question, whereby they want you to derive the pressure of an ideal gas. Now, in order to do this question, right, we need to do a little bit of definition, which means to say that we need to define something. Okay, so first things here, let's first consider one molecule of gas with mass m that is moving at a speed of cx in the x direction. Okay, so let's just assume that your gas is actually moving in the x direction and it has a speed cx. Okay, and it is hitting the wall of the container, elastic collision. Because if you want to actually find the pressure, you will need to find, that means that the gas molecules are actually hitting the walls of the container, since pressure is force per unit area. Understand? So, if we assume that the collision is elastic in the case of ideal gas, then we can find out what is the force exerted by the wall on the molecule. Okay, since the molecule is exerting a force on the wall will also exert the same force on the molecule, which is actually the change in momentum divided by time. Okay, so how do we actually calculate this? Since net force acting on by the wall is actually equals to the rate of change of momentum. So the change in momentum is actually equivalent to 2 times the mass and the speed. Why? Because your object is hitting onto the wall, then bouncing back with the same speed, just that it's in the opposite direction. So the mass is the same, so 2 times. And then the time taken is actually the time taken for the object, for the gas, okay, molecule, to travel from one end of the container, okay, of length L, from here to here, to the other end of the container, and then bounce back again. Understand? So therefore, the distance traveled will be 2L. And since the speed is cx, dividing it with the speed will give me the time. So then the force exerted by this one molecule will be equals to this. And that is the same amount of force that the wall exerts on the molecule. Okay? So if I were to quote by Newton's third law, we can then say that the force exerted by the wall on molecule is equals to force exerted by molecule on wall. So therefore, we can say that the force that is exerted on wall by the molecule is equals to mcx squared divided by L. Okay? But this is only one molecule. Now, in an ideal gas, or rather in any gas, there is more than one molecule. So therefore, the force exerted by the gas on the wall is therefore equals to n times of all the molecules times the mass of all the molecule times the mean square speed, because all the gas molecules or atoms, whatever the gas is traveling at different speed. It is not possible to just use one speed of the molecule. Therefore, we need to use the mean square speed of the molecule, which is their average, and then divided by L. Okay? So then how do we then calculate this? So we say, since there are a large number of molecules moving in random motion, okay, to calculate all the mean square speed of the molecules in moving in the x direction will be the same as the mean square speed of all the molecules moving in the y direction and the mean square speed of all the molecules moving in the x direction. Do you agree? Because the molecules are moving the same in all directions. We cannot just say they're only moving in x direction. So to calculate the average of all of these, okay, it will just be the sum of all their square speed in the different direction, divide by 3. Okay? So we have gotten the force, we have gotten the speed. And therefore, if we were to actually calculate the pressure, we know that pressure is actually force divided by area, and the area of the cubic container would be L squared since it's a cubic container, and therefore this would be 1/3 nm delta the average of c squared divided by L cubed. Okay, so then from there I can just simplify. This whole thing here will just be equals to my density, because it's mass over volume. So then would be, sure. Do you understand? Okay. For this question here, the mark allocation is 1, 2, 3, 4. 4 marks for derivative question. Okay. They award 4 marks for this question. So if you come across any derivative portion of your notes, right, don't just skip them and learn the final formula, because sometimes they will actually test you on how to derive the working at the end, or the question at the end. So understand how they get the formula. Okay? For this one, it's just a very simple concept of pressure equals to force over area. The hard part is, how did we get the force? So we started off with force being the rate of change in momentum. Then using this rate of change in momentum to introduce the speed inside. But we first fix the speed in one direction. Then once we find the speed of one molecule, multiply it with all the molecules to get for the gas. Then find the average speed traveling in all directions. Then finally put everything inside the pressure, the basic pressure formula. Okay? Okay, now the next one, explain what is meant by the latent heat of fusion. So this one is a secondary school question. So I just quickly go through. Latent heat of fusion. Okay, when you see latent heat of fusion, it means there is a change in state, not the one change in temperature. So this one you have to mention what change of state is happening, and ensure that you always write down the keyword, there is no change in temperature. That's the key point, understand? Okay, so Latent heat of fusion is the amount of thermal energy required. Now, because it's specific means per unit mass. If they don't add the word specific, means no per unit mass of a substance to change it from the solid state to the liquid state without, so this is the key phrase, any change in temperature. Okay, so this is the latent heat of fusion definition. Very quick and easy. So now the next part. A thermally insulated vessel containing liquid water and water vapor is connected to a vacuum pump that removes water vapor continuously. When the temperature reaches the freezing point of water, the vessel contains 120 grams of water and the specific latent heat of fusion of water given to be this, specific latent heat of vaporization of water given to be this. Calculate the mass of ice formed when no liquid remains. So we need to understand the process that is happening here. You have liquid water and water vapor, and the water vapor is continuously being pumped out by a vacuum pump. So technically means you have liquid water. When the liquid water reaches the freezing point, then you realize that there is 120 grams of liquid water. So why is there specific heat of fusion of water given? Because quite obvious, this shows you the hint that your liquid water is actually changing to ice, change in state, right? Then why did they give you the specific latent heat of vaporization of water? Usually this means gas to liquid or liquid to gas. And in this case here, we realize that there is actually a change from gas, which is your water vapor, changing into water. Okay? And why must that happen? So that later your water can then change into ice. So that's why the water vapor is here. Okay? So how do we do this question? Since we already understand the flow of process, they want us to find the mass of ice formed. So we say, let the mass of ice formed be m. Okay, small m. Now, they said that there is 120 grams of liquid water. So we write here first the initial mass of liquid water is equals to capital M 120 grams. Okay. So there is ice that is being formed. So we can, and if ice is being formed, means there is ice losing heat. It means your water have to lose heat in order to form ice. So the heat loss forming ice must be equals to somebody is losing heat, somebody must be gaining heat. And in this case here, the heat gain is through the evaporation process whereby the vacuum pump is removing water vapor. Okay, so therefore it is equals to the heat removed by evaporation. So forming ice, evaporation, all these are state processes. Change in state, change in state. So the formula we use will therefore be Q equals to ML something. For ice wise, MLF. For evaporation wise, MLV. However, what is my M here? My M is not the total 120 grams of liquid water being evaporated, but rather the amount of initial mass of water present minus away the water that is used to form the ice. Because the water that evaporated or rather became liquid water will be the one that is used to form the ice. Understand? So then this will be LV. So to find small m, all I got to do is just take LV over LV plus LF times capital M. Okay, all I got to do is just make m small m the subject of formula. Then from here I put in the values 2.52 times 10 to the power 5 over 2.52 times 10 to the power 5 plus 3.40 times 10 to the power 5. So please 10 to the power 5. then times the mass, 120 grams. Since everything is in gram, take note. Wait, I need to divide it by 1000 because everything is in kg and this is in gram. So 120 divided by 1000. Then this would be 105.7 gram, approximately 106 gram. Okay? Okay, so that's one question. Now, the next question, question 2a. Okay, for this question here, it says, state what does it mean by an ideal gas? So, in order to actually write the definition for an ideal gas, I think most of you guys would have already known that an ideal gas equation, ideal gas is basically one that obeys the ideal gas equation, right? Okay, so in this case, the ideal gas equation is equivalent to PV equals to nRT. So you need to mention that inside your, you don't have to mention that, but you have to at least say that an ideal gas obeys the ideal gas equation and a few other conditions as well. Okay, so we say that an ideal gas is actually a hypothetical gas. Why is it hypothetical? Because it doesn't exist in real life. Okay, and in order for a gas to be an ideal gas, the molecules need to occupy negligible space and have no intermolecular interactions between each other. And it also obeys the ideal, actually don't say ideal gas, the gas laws, exactly at all pressure, volume, and temperature. Okay, so this is the definition for an ideal gas, and this is what it meant when they say what is an ideal gas. Okay, the next one. So question 2. Now they say I have an ideal gas that comprising only a single atom, so there's no molecule, is inside a cylinder which has a volume of this and at a pressure of this. So you have your P, you have your V. Now the mass of the gas is given to be 3.2. The mass of the gas in the cylinder is 3.2 kg, so you have your M as well. Determine the root mean square speed of the atoms of the gas. Root mean square speed means what? They want the square root V root mean square, this. Okay, or essentially they want the V root mean square. Okay, now how do we do this? We know that from the kinetic theory of gases, if I want speed means I have to use kinetic energy. And for an ideal gas, kinetic energy of ideal gas is equivalent to 3/2 nRT or N capital NKT. Okay, so then we also know that for ideal gas equation, PV is equals to nRT. So what does that mean? This means that if I were to sub both of them together, my kinetic gas is half m root mean square speed is equals to 3/2 PV. Make sense? I'll just substitute this inside. Okay? Okay, so then from there, what happens is that to find my VRMS square, I will actually have times 2, so I will have 3 PV divided by m. And therefore, my root mean square will be square root 3 PV divided by m. And since I have all the values, all I got to do is just sub in the values inside. So square root 3, my pressure is 2.12 times 10 to the power 7. My volume is 1.84 times 10 to the power negative 2. And my mass here is 3.20. So this gives me the root mean square of 605 meters per second. Okay? Okay, next 2C. The temperature of the gas in the cylinder is 22 degrees Celsius. Now, in physics, we don't use degrees Celsius, we use Kelvin. So make sure you add a 273 at the end. Okay, when you want to use calculation, determine the amount of gas. When they ask for this question, usually they meant number of moles. So how do we find the number of moles of gas in terms of amount of gas? We therefore, the only formula that you know is PV equals to nRT. So then they have given the P earlier on already. The V, R is a constant, temperature is also given here. You can calculate your N. You take PV divided by RT. So P is 2.12 times 10 to the power 7. Volume is 1.84 times 10 to the power negative 2. Divided by, my R is my constant, my gas constant, 8.31. 22 plus 273. So this will give you N to be 159 moles. Okay? Then once I got the amount of gases in terms of mole, I can find the mass of one atom of the gas. How do I find the mass of one atom of the gas? I know that the mass of the gas, based on chemistry, is the number of moles of gas times the molecular mass of the gas, correct? Okay, but because I don't have the molecular mass because I don't know what gas it is, the only way for me to calculate this is actually to get the number of atoms inside the gas times the mass of one atom. Okay, so I want to find the mass of one atom. Therefore, the mass of one atom is taken to be the mass of the gas divided by the number of atoms. Now, how do I get that? The mass of the gas was given earlier on to be 3.2 kg here. So therefore, in my formula, I just have to equate it to 3.2, and the number of molecules can be calculated by taking my number of moles times Avogadro's constant. So 159 times 6.02 times 10 to the power 23. So therefore, this will give you the mass of one atom to be 3.34 times 10 to the power negative 26 kg. So that's your final answer for part 2. Okay. So once you have the mass of one atom, now they say use your answer in part 2 to determine the nucleon number of an atom, meaning the number of protons plus neutrons. So that means the MR, right? So how do we determine the MR from the mass of the gas? We can say that the mass of an atom is actually equals to the nucleon number times the unified atomic mass, basically the mass of one atom. That means the mass of one subatomic particle, like what's the mass of one proton and what's the mass of one neutron. Okay, so that gives me the mass of an atom. So my nucleon number is what I want to find. Therefore, my nucleon number is equals to the mass of atom divided by the unified atomic mass, which is given in your data booklet. This one, the mass of one atom, one proton or neutron. And the mass of an atom earlier on we have found 3.34 times 10 to the power negative 26 divided by one proton or one neutron is given to be 1.66 times 10 to the power negative 27 kg. So then when we divide them together, we get a mass number of 20. Okay? Yeah. Okay, so this is for temperature ideal gases. Okay, the PV diagram, that one should be quite straightforward. Just make sure you always use your first law of thermodynamics to calculate your delta U, and then follow the signs correctly, then it should be easily done. Remember the special processes for your PV diagrams, so you can also calculate your determine who is going to be set 0, who is going to be set constant. Okay, the next one we're going to move on is oscillation. Oscillation for this one includes your simple harmonic motion. So take note, for simple harmonic motion, whenever they ask you for the definition for simple harmonic motion, make sure you define it as an periodic or oscillation. Periodic oscillation means it happens at regular interval and it keeps repeating, whose acceleration is directly proportional to the displacement and is directed towards the equilibrium position, meaning directed opposite to that of the displacement. So once you actually have these definitions set properly, you are able to come up with the simple harmonic motion defining equation. And in this case here, simple harmonic motion is actually this equation. A is negative omega square x square, omega square x, whereby x is actually the distance from the equilibrium position and omega is your angular velocity. So I mentioned here, angular velocity is different from angular frequency, not angular velocity. Angular frequency is different from frequency. Don't mix them up. Angular frequency unit is per radian. Okay, but frequency's unit is in hertz. Okay, then for simple harmonic motion, the velocity equation will always be given as this, whereby your velocity is varying between the positive or the negative direction. Then your angular frequency times square root the distance, original distance of your motion squared minus the change in displacement of your object from the equilibrium position squared. Okay? So if let's say we were to find the maximum velocity, this is plus minus omega x naught. Why? Because in maximum velocity wise, there is the displacement from the equilibrium position is 0, given that it does not displace away from the equilibrium position. So if this is 0, you are square rooting your x naught square. Hence, maximum velocity will always give you omega x naught. And omega is given by the formula 2 pi over t or 2 pi times frequency, since 1 over t gives you the frequency. Understand? Okay, so these are the key things you need to know for simple harmonic motion. Now, the next thing you need to take note of is the graphs. So if let's say they were to ask you about the graphs for your simple harmonic motion, your acceleration versus your displacement, that's when you realize that acceleration is always directly proportional to your displacement, just that it is in a negative gradient. So therefore, you will have one straight line slope like that. It's a linear equation. Understand? But if I were to vary my velocity with x, then it would be a circular shape, whereby the maximum velocity is omega x naught, and then the maximum amplitude is, in this case here, x naught. Okay? Okay, then next, the kinematics of a simple harmonic motion, meaning to say that how does my values of my simple harmonic motion changes accordingly. So one important thing I need you guys to take note is this. The equations are only applicable when we start at t equals to 0. So for whatever we are looking here, right, is when t equals to 0. And if let's say my oscillation starts at t equals to 0, that means my displacement is the maximum, then I will start off with the cosine function. Okay, that means you are already at the amplitude portion of your oscillation. Then you start with here, x equals to x naught cosine omega t. Okay, now to change from displacement to velocity, what we need to do is we need to differentiate. Okay, so if we were to differentiate our displacement, you realize that my velocity, let's say for cosine, will become negative sine. You see that? And the equation for acceleration will become negative cosine back. And if this is equals to x, that means x naught cosine omega t equals to x. And therefore, I can change this to negative omega square x. Okay, so this, at the end of the day, you realize still obeys the simple harmonic motion equation. Now, if let's say my oscillation doesn't start off at the maximum displacement, meaning it's not at the amplitude, but it's in the middle, whereby it's at the equilibrium position, then we use x equals to x naught sine omega t. Okay, differentiate sine omega t will give you cosine, and that's why your velocity will have negative, omega x naught cosine omega t. Then differentiate my velocity to get my acceleration will give me negative omega square x naught sine omega t. Then you realize this represents x, which means at the end of the day, you still get back your simple harmonic motion equation. Okay? So understanding these values is important. Why? Because knowing the velocity can give you the equation for kinetic energy, which then allows you to draw the graphs for kinetic energy. Yeah? Okay, then tip 3, we're going to revise quickly on damped oscillation. For damped oscillation wise, any oscillation that has external forces acting on it or restrictive forces acting on it will be considered a damped oscillation. 3 types of damping: light, critical, heavy, if you guys still remember. Light damping is like the kind where you swing your door, right? And then after that your door just keeps swinging. It's like a very loose door, then you just keep swinging. So that kind of oscillation, we call it light damping. This kind of damping, right, the amplitude decreases gradually over time. So for them to return to equilibrium, it needs a very, very long time. Critical damping is the kind I think most of your lecture halls have, or in your JC, where you open the door, then after that you enter into the lecture hall, then the door swing quickly first, then after that suddenly slows down, then close up. Okay, so that's because your door has a damper on top, that silver box thingy near the door. That's actually a damper that provides critical damping to your door so that it changes the amplitude really quickly, not allowing the body to oscillate, and return it to the equilibrium position the shortest time possible. Okay, so I give you guys one example already, which is actually the your lecture doors in your school. Another example is the car suspension system, because imagine you're going to see a car whereby the damping is not critical. What happens is when the car goes over a hump, you start to oscillate up and down, up and down. It's going to make you very dizzy. Okay, so car suspension system has critical damping to make sure that the car don't oscillate that much, but at the same time return to the equilibrium position as fast as possible. Now the last one is heavy damping. The graph looks something like this. For this type of damping, the body will take a really long time to return to equilibrium without oscillation. Okay, so this is what we call heavy damping. Now, how does then this damping affect, in that case, my resonance? So you all know that resonance means that it happens when your driver frequency is actually equivalent to your natural frequency. And when that happens, the amplitude is actually the peak. Can you see that? Which means that your object will now oscillate at the maximum amplitude. And amplitude is related to energy, which means to say that your oscillation is happening at the greatest energy. So it might cause some catastrophic event happening. So what happens if we apply damping to my system? How does it affect my resonance? You realize that with light damping, the resonance peak. Without damping, there is actually infinite resonance. You can see that it goes up to infinity. Okay, but that doesn't happen in real life, because in reality, there is at least a little bit of damping that is happening in any oscillation. So light damping is the closest that we can get. But as my damping becomes heavier and heavier, you realize that the peak starts to become smaller and smaller. And not only that, it happens earlier, which means that it does not need to meet the driver's frequency, then the resonance will actually happen. Okay, so if you want to prevent a system from oscillating too much and as a result breaking, you will therefore have to apply damping to the system because it brings down the resonance amplitude. Okay? Okay, so here, what does it mean by a damped oscillation? In this case here, damped oscillation, just pretty straightforward. Say that a damped oscillation refers to the oscillator's energy being dissipated. Okay, causing the amplitude of the oscillation to decrease over time. Okay, so this is what a damped oscillation is. Keyword, make sure you mention that the amplitude of the oscillation decreases over time. Huh? Okay, now, next one. The figure shows a spring mass system, a very popular system that they like to test. Hanging vertically from a fixed support, the mass is displaced vertically upwards by 3 cm. Released to vibrate, simple harmonic motion. So that's the key for you to be able to use your simple harmonic equation already. And then they gave you the period t. So you have t and you have your displacement x as well, right? The effect of air resistance is neglected, so calculate the magnitude of the maximum acceleration. So a lot of things they gave you. You have the equation A equals to negative omega square x. Then you want to calculate maximum acceleration. This means to say that your A max can be calculated by taking negative, since magnitude, right? So I ignore the signs at the end of the day. So I just modulus this part here. Now omega is 2 pi over t square, correct? And then this is my x. Then I just got to sub in the values, negative 2 pi over 2.0 square times. Now my x is in cm, make sure everything is in SI unit. So you need to convert this into meters, which is 3.0 times 10 to the power negative 2. Then modulus this part as well, because we only want the magnitude, okay, as stated here. So this will give you an acceleration of 0.296 meters per second square. So this is the maximum acceleration of your mass spring system. Okay. Okay, then part 2. The same mass spring system is now displaced vertically upwards again and released to oscillate within low viscosity oil. Meaning to say that these oils will cause your spring system to move slower, but not that slow, because the frictional force is not that high as well. But there is still frictional force. Sketch on the axis the variation of displacement with time of the mass oscillating in the oil. So this is the displacement time graph, which essentially means they are looking for your amplitude time graph. How is your amplitude changing with respect to time? So low viscosity is a hint to you that this is light damping. Understand? So all you got to do is just draw a light damping diagram. But because they gave you values, you need to make sure your diagram is somewhat accurate in terms of value-wise. They have mentioned earlier on, maximum amplitude stretch is 3, period is 2. That means with regards to your graph-wise, you need to make sure that it first starts off at 3.0. You understand? And then for every one oscillation, my drawing is really bad, but I hope you guys get the gist. Just make sure that your amplitude is decreasing every time you draw the graph. Okay? Then every one oscillation here, this is 2.0 second. One oscillation, 4.0, 6.0, something like that. Okay? And just have to make sure that your amplitude is decreasing over time. Okay? Okay, now the next one. The same mass spring system in B part 1 now. So they changed. They took out the oil. They replaced it with a movable support. So that means this support here can actually move. Air resistance is neglected and a periodic force is now applied to the support such that the mass undergoes force oscillation with very large amplitude. This is quite obvious already. Support movable. This is actually your driver. Can you see that? Your driver is the one that provides the driver frequency, hence causing it to undergo force oscillation and large amplitude resonance. So state the physical phenomena that is associated with this and the condition necessary for this to take place. So I've already mentioned the physical phenomena would be resonance. Okay. And the conditions for this to take place would be that the driver frequency needs to be equals to the driving frequency equals to the natural frequency of the spring mass system. Okay, so it's not that hard, just have to pick up keywords from your question. Okay, good. Now the next one. A car suspension system helps to damp its vertical oscillation. So you have a car suspension system here. And we've seen earlier on that the car suspension system is actually a critical damping system because you don't want the car to oscillate that much and you want it to return to the equilibrium really quickly. State the type of damping and the importance of such damping for a working car suspension system. So, as I have mentioned, it is critical damping. Okay, is required for a car suspension system. And then why is this necessary? So this is necessary to stop the car from oscillating as quickly as possible that could otherwise cause the driver to lose control of the car. Okay, and it also prevents excessive discomfort to the passengers in the car. Okay, I'm not sure whether you guys have sat in a car that has very bad damping system, but one of the vehicle that I sat on is the red color taxi that brand. Their cars have very bad suspension system, so every time it goes past a hump, right, the car will just keep oscillating really badly. Okay, so this is for oscillation with regards to the damping portion, okay? As well as with regards to mass spring system and SHM. Now, the next thing we're going to look at now is actually in terms of waves, superposition. So for superposition, let's just recap. The most important thing you need to know is how do you define principle of superposition? It is when two or more waves, same nature means same type, meet at a point, and then the resultant displacement will always be a vector sum of the individual displacement. Take note, it's a vector sum. So the two waves must be of the same type, and if they are transverse wave, they must have the same polarization of direction, and the intensity of the wave have to depend only on the magnitude of the wave, as intensity is directly proportional to square the amplitude for principle of superposition wise. Okay, so then in superposition, one of the application is interference. So you need to actually recap interference wise, whereby there are two interference happens when you have two or more waves of the same time superpositioning to produce a resultant wave. And these resultant waves produces either constructive or destructive interference. So constructive interference is whereby they meet at the same point to produce a wave of even larger amplitude. But destructive interference is they cancel each other. At the end of the day, your resultant wave is zero. Okay? So for constructive interference and destructive interference, there are different portion or different times when that happen. You can determine whether it's constructive or destructive interference, you need to first determine whether your sources are in phase or out of phase. Okay? Usually they will tell you. Otherwise, you can actually find out by calculating, looking at their graphs or by calculating their time differences. Okay? So if the two sources are in phase, a constructive interference happens when their path difference is multiples of their wavelength. Okay, so that means they will meet in phase. But a destructive interference will form where the path difference is half of the odd multiplication of your wavelength. That means your waves will meet out of phase. Okay, but if let's say they were anti-phase, that means originally your source is actually not meeting each other already, then it will be swapped. Destructive interference will happen when the path difference is a multiple of your wavelength, and constructive interference will form when it is actually the half of the multiples of your wavelength. Okay, so the next application for superposition would also be, or interference would be when you have a single slit difference. So for this type of question, right, always identify your question first. Is it a single slit or a double slit? Because if it's a single slit, the only formula that you can use here would be d sine theta equals to m lambda, where m is the number of fringes that you have. So usually we calculate the central to be 0, then this is m equals to 1, m equals to 2, then m equals to 3, so on and so forth. And this is m equals to 1 as well, m equals to 2, m equals to 3. Understand? So in single slit interference, you will see that the wave will pass through an aperture, which is a hole, okay, in a slit, which will then cause them to diffract. And then when they are hit onto a screen, they will produce a fringe pattern as shown like this. So the bright spots or the bright region, we call it the maxima, means that there is constructive interference. The dark spots, in which we call the minima, is where there's a destructive interference. Understand? So at the end of the day, you will have this formula, d sine theta equals to m lambda. Otherwise, you can also use d sine theta equals to n lambda, where n is the number of order of your bright fringes. It's the same formula. Okay? Now, what happens when you have a double slit diffraction? Now, for double slit diffraction, you will have a light source first, having one slit here to diffract your light source into single fractions. Then after that, you place a double slit with two apertures to actually produce two different waves of the same type. Then when they come across, when they superpose at this part here, all the cross parts, they will produce regions of bright, dark, bright, dark, bright, dark. So the bright images is where constructive interference happen and the amplitude is the highest. The destructive interference is where you have the dark fringes and there is no amplitude happening. Understand? Okay. So, like I said, constructive interference, bright fringes, destructive interference, dark fringes. Okay? Now, for this type of double slit experiment, the formula you use would be the fringe separation is equals to the wavelength of the light times the distance between the slit and the screen divided by the slit separation. Okay, which means to say that 0 here, intensity wise, this is how we draw it. You will see that at the 0 central point, the intensity is the highest. Then as you spread out, the intensity goes in waves like that. Understand? Okay. So if we combine everything together, you can see when I have a maxima, means constructive interference, my path difference will be just 1 time the wavelength. But if I have the second maxima, it will be 2 times the wavelength, which is n lambda. But right now, I'm assuming that the particles are the sources are in phase. Okay. If let's say we're talking about the first minima, then it will be half of my wavelength, 1.5 of my wavelength. So that's how we incorporate the interference concept into your double slit diffraction. Okay, so let's go through one question. Now it says, state what does it mean by coherent sources. So this one you guys should know how to answer it. It's just definition. So coherence just means that the phase difference between two waves remain constant and do not vary with time. Okay? So that's what coherence is. Now, let's take a look at the next question. So I have two coherent microwaves, meaning to say that their phase difference is always constant. They don't change in between. S1 and S2, then they tell us they're in phase. So this is an in-phase light source with each other. They emit wave of equal frequency, equal intensity, same direction of polarization. So superposition can happen. Okay? Now, a microwave detector is detected at point P. So you have a detector here. The initial distance of S1 and S2 are equal. So it's like an isosceles triangle. They are equal distance from each other. And the intensity are both given as L. Okay. Now, they say S1 is slowly moving away. So S1 is moving back as shown. How does the intensity of the microwave changes detected at P is going to change? So, you know that this is a superposition question together with an interference question. Okay? So, as such, you will need to actually marry these two concepts together. Now, obviously, right, you know that as your S1 moves to the back, the path difference between S1 and S2 is going to be different already because initially they are equal. Now one side is going to be longer than the other. Okay, so your intensity of the microwave will start to change accordingly. Now, how do we do that? How do we explain this? For this, in this case here, we will say, I don't know why I cannot type. Oh no. Okay, now, so we say the microwaves from the two source, the microwave waves. From the two sources undergo interference. Okay, the path difference between S1 and S2 changes as S1 moves. Okay, so then it changes, but it doesn't stay constant at 1 because it alternates between constructive and destructive interference. So you have to actually explain both. So when the waves are in phase at P, the path difference between the sources, so I'm going to write in short form because I don't really have space, is an integer number of their wavelengths. So then we say constructive interference will occur at P, resulting in maximum intensity. Okay, so this is for what happens if there is a constructive interference. Then for destructive interference, we say when waves are at antiphase, at P, the path difference is an integer number of wavelengths plus half a wavelength. So then destructive interference occurs at P, resulting in 0 amplitude. Intensity, don't use amplitude. Okay, so this is how we explain what happens, what is being detected at the microwave at P there. Understand? Okay, so the first thing you need to always remember is make sure you find out whether they are in phase or antiphase. Then once you find out whether they are in phase or antiphase, then you can determine whether is it constructive based on the path difference. Okay, now the next one, part 2. S1 is moved from point X to Y as the intensity of the microwave changes from maximum to minimum. So from X to Y. So at X here, it's a maximum intensity. Minimum means constructive to destructive. And the distance of XY is 8.2. Calculate the frequency of the microwave emitted. So I need the frequency, and I know the path difference in this case here is changing from maximum to minimum, which means half the wavelength. That's the difference, correct? Because if you remember, for constructive interference is n lambda, for destructive interference is n plus half lambda. So the difference between them, okay, I just put delta D, would be half lambda. So in this case here, my path difference is actually half lambda, and it's actually equals to 8.2, since they said that this is the change in path, right? So my wavelength here is equals to 0.8.2 times 2, but then change it into meters, so divide by 100 equals to 0.164 meters. Then because they are waves, microwaves even, we know V equals to F lambda, right? And in all vacuum, they will travel at the speed of light. So frequency is V over lambda, which is 3.0 times 10 to the power 8 divided by the wavelength, 0.164, to give us 1.8 times 10 to the power 9 hertz. Okay? Okay, next, S1 remains at point Y. So S1 remains at this point here. And then they say that a polarizer now is placed between S1 and P. The direction of the polarization of the microwave is changed by 40 degrees. So they turn the polarizer by 40 degrees, and the power is adjusted such that the intensity remains as L. So when you change the polarization of your S1, it changes the angle of your wave. And when your angle of the wave is changed, what happens is that some of your microwave will actually be blocked by the polarizer. So the power and the intensity of the wave will actually be affected. But to make sure that the intensity remains the same, you therefore need to change the power. So then they say explain without calculating what the intensity of P will be like. Okay? So how do we explain for this one? Like I said earlier on. So we explain by saying as the microwave from S1 and S2 are no longer having the same axis of polarization, destructive interference does not take place. Okay, meaning to say that now your waves are completely out of phase from each other. So you won't have one wave that is going up and then the other wave that is going down to balance each other. Even if destructive interference takes place, right, there will be a little part of your graph that has little resultant amplitude. Okay, that's why they say destructive interference does not take place, and hence the waves don't cancel out. So therefore, the intensity of the microwave at P is now between the maximum and minimum intensity. Okay, hopefully you all understand this part. Because my polarization is not changed by 180 degree or 90 degree, it's changed by 40 degree. So your wave is kind of like slanted. So they won't have a region whereby it's maximum or minimum only, like they completely cancel or they completely add. It will be the in-between of maximum and minimum. Okay, now next. The figure here shows the variation of the displacement of the microwave from S2 now to P. So they're saying that S2 displaced out to P, right? The displacement is by this amount of units. The polarizer in B part 2 is now removed, and the intensity of the microwave at S1 is reduced to half the intensity. Show that the amplitude of the microwave from S1 now is approximately 8.5. Now, how do we show the amplitude? That means I'm looking for 8. So, remember they said that S1 and S2 are actually the same type of waves earlier on. They said that they are in phase, they emit waves of equal frequency, equal intensity, and equal direction of polarization. So if this is for S2, I can actually calculate from the bottom here, 6, 7, 8, 9, 10, 11, 12, that the original amplitude of S1 is actually 12 units. It's the same as the amplitude of S2. Okay? So, remember intensity is directly proportional to amplitude. So in this case here, what would be my new amplitude of S1? Since that my intensity of S1 is now reduced by half, it will be square root half of my intensity divided by my original intensity, which is actually 12 units. Then from here, I'll get 8.5 units squared. Units, understand? So then to draw the variation, all I got to do is just draw 8.5 units. So 1, 2, 3, 4, 5, 6, 7, 8.5. So it's somewhere here. Then 1, 2, 1, 2, 3, 4, 5, 6, 7, 8.5. So it's somewhere here. And then after that, it's somewhere here as well. Okay. So I'm just going to draw. They still cut at the same axis, just that now they have smaller amplitude. Okay. Okay. Now, the next one. Let's go through the revision for current, electricity, as well as DC circuit really quickly. In current, electricity, and DC circuit, right? What happens is that we need to understand the new concept of internal resistance. Because when we talk about current electricity, it's just your current, potential difference, resistance, so on and so forth. So in this case here, we need to learn this new part of internal resistance, whereby we use this formula to calculate that. Take note, the EMF of your battery or your entire source is actually made up of the total potential difference, or the potential of your battery plus the potential of your internal resistance of the battery. Okay, and if we were to then use the power formula whereby we include it into IE, then it's actually the same as I square R times I square small r. Okay, then to find the voltage terminal voltage, because that is what is the only terminal voltage is the voltage that comes out to power all your appliances outside, we will then only use IR here, which is taking the total EMF of your battery minus IR. Okay, so the internal resistance that is present will cause your terminal voltage to actually be lower than the actual EMF of the battery, and hence the actual power output to be lower than the theoretical power output. So how do we then measure internal resistance? Just keep in mind, if let's say, right, your switch here is open, you will always have a voltmeter here, and this voltmeter will then measure the EMF of the source, which is the EMF of the battery here, the whole thing. Okay, because when the switch is open, what happens is that current cannot flow through. Current cannot flow through, your internal resistance cannot work. Sort of like doesn't have electricity flowing through, so doesn't have potential difference. So therefore, it will just solely depend on the battery. But now when the switch is closed, current can start to flow in the circuit. And when that happens, your voltage will actually read the terminal voltage of the source. Understand? And your ammeter measures the current in the circuit. Okay? So then next, potential divider. For potential divider, just take note, in potential divider question, you always have a series circuit, and the potential is divided by using resistance in this case here, whereby it is split up into different voltage output based on the resistance. So if let's say I want to find the voltage output here across resistance R1, then I will use the formula. The voltage output is equivalent to R1 divided by the total resistance that is added in series times the total voltage. And the total voltage in here usually refers to your EMF, as mentioned here. Okay? Whereas for potentiometer, it is similar to your potential divider, just that instead of using a fixed resistance, we use a straight line of wire, because wire carry resistance. And this type of device, right, we can vary the length of the wire to vary the voltage output, which means to say that the voltage output is actually dependent on the ratio of the resistance of the wire with respect to the original length of the wire, and the ratio of the length that I want to clip at versus the original length of the wire. Okay? Okay, then the more popular one is this thing here called the balance point, whereby when we talk about balance point, right, this is the point or the contact point on your line, on your potentiometer, where the test cell nullify, meaning to say that there will not be any deflection in your galvanometer. And when there is no deflection in your galvanometer, just remember that the voltage measured across here will be equivalent to the EMF of your driver cell. Okay? So, in that case, the formula to use is I can make use of the length of the test wire that I use over the original length, the total length, to be equals to the voltage output over the total voltage across AC. Okay? Okay, just take note, at the balance point, even though there is no current flowing through the circuit in the lower circuit here because the deflection is null, there is still constant current flowing in the main circuit here. Okay, that's how you can measure the EMF. And in the test cell, the internal resistance, if there is any of the external test cell, does not matter because at the balance point, no current flow through, there will not be any potential drop should there be an internal resistance here. Okay? Okay, so let's quickly take a look at question 5. Now it says here, for question 5, the variation with potential difference of a current of a semiconductor diode is as shown below. And in this case here, they want you to use the figure to describe the resistance of the semiconductor diode between negative 0.5 volt to 0.8 volt. So for this question here, it's very straightforward. Just look at the diagram. You can see that from 0.5 to 0.8, initially from negative 0.5 to 0.5, there is no resistance, but as the voltage starts to, no current, that means it's high resistance. But as the voltage starts to increase, the current starts to increase, which means more current is flowing through, so there will be lesser resistance. Understand? So we say that at first, there is very high, or in fact, infinite resistance for negative voltage, just up to 0.4 volt. Okay, then as you increase beyond 0.4, your resistance starts to decrease from 0.4 volt onwards. Okay, how do I know my resistance decrease? I make use of the current to determine. Okay. Now take note, you need to give them values because they actually say based on the figure. So if you don't give them any values, they will not give you the mark. Okay. Okay, the next one. Determine the resistance of the diode at the instance when current is equals to 0.4 milliampere. So very quickly, just read off from the graph. When current is equals to 0.4 milliampere, what happens is that your voltage is equals to 0.55 volt. So to calculate resistance, 0.55 volt divided by your current, which is 0.4 times 10 to the power of negative 3. So you get 1,380 ohm. Understand? So just got to read from your graph, 0.4 milliampere, somewhere around here. Okay, next one. Now sketch the variation of a potential difference with current for a filament lamp. Filament lamp, you need to remember that the resistance will keep on increasing at high voltage because of the increase in temperature inside your filament lamp. So because there's an increase in temperature, higher resistance, so the current will start to decrease. The current that can flow through, more current that can flow through will decrease. So that's why the current will approach sort of like a plateau at the end. So that's for filament lamp. Okay. The next one, I have a power supply here, EMF of 12 volt, internal resistance 0.5, connected to a lamp, a variable resistor, and a switch. Now the switch is closed and the filament lamp has a power of 20, potential difference is 10. Power, potential difference, calculate resistance. So the formula is just power equals to V square over R. 20 equals to 10 square over R. R is equals to 5.0 ohm. Okay, so that's how we calculate the resistance of the lamp. Okay, then they say the variable resistor is now adjusted to 2.0 ohm. Potential difference is 20 volt. Calculate the resistance of the lamp. So for this concept, we can actually use the potential divider principle. Because now we are varying our resistance, to vary our potential difference. So the resistance is what I want to find. It's the resistance of the lamp plus the variable resistor plus the internal resistor. So don't forget to add the internal resistance of the battery, then times 12 volt. So my resistance of my lamp is actually 2, then which is equals to 2.0 ohm. Then from there, I can calculate my resistance of my lamp to be 0.5 ohm. Okay, why is it 2.0? Because it said the potential is 2.0. Okay, then the last part, describe how the two values of resistance calculated provided evidence for the shape of the sketch you have formed. You can see that there's the sketch. As I increase, when I add in the lamp here, you'll realize that my resistance actually decreased. Okay, so that 5.0 ohm to then 0.5 ohm. Okay, so as your voltage increases, your resistance decreases. As your voltage decreases, your resistance increases. So we say that the resistance of the lamp increases as the voltage increases. Okay, which makes sense of the sketch going in a increasing and a decreasing rate kind of graph. Clear? Okay. So hopefully you guys can learn something today, at least in this revision here. So as usual, whatever is taught here is on the curated notes. If you all want to learn more work example as well as tips, then you all can buy the curated note. The QR code is there. It's actually a very good set of notes because all the key concept, all the tips are inside. You don't have to lug all your lecture notes, which sometimes can be very confusing. Okay, and if you need more help, actually I want you guys to pay attention more to the crash courses because we're going to have crash courses this June holiday to prepare you guys for your, not only your mid-year, but your prelims as well. Okay, so there will be 3 modules. If you for J2s, right, we'll be covering everything for June. So it's a 4-hour session each time, but it's an intense 4 hours. So hopefully we can finish everything. And if possible, I can also clear nuclear physics, which I don't think the school will cover yet by June, but hopefully we just finish everything during the crash course. So any questions you all have, you all can also bring it down so that you all can clarify with me during the crash course. Okay, so if you want to sign up, the QR code is there. You all can just sign up from there. Can? Okay. So hopefully you guys learned something today for the mid-year revision. Then if there's nothing else, you guys can leave the meeting and good luck for your exams and revision. Okay. Bye-bye.